Good morning, Irvine.
Good morning. Good morning.
Happy day to everybody. Yes. Are we all charged up? Okay. And in the quiz you just took, one of the things that you used quite a bit of was memory, right? Okay, and I'm sure the grader for the quiz will say thanks for the memory. And memory, what does memory consist of? Thoughts. I can have thoughts that aren't memory, and I can have thoughts that are part of memory, right? So what's the, keep going. Say a little louder.
Working memory versus long-term memory.
Okay, so working memory, long-term memory implies what about memory? What is it? Okay.
Memory at one point needs to get converted into long-term memory.
Let's do some physical stuff here. Does memory happen from here below or here up?
Above.
Up. Where? On here?
Brain.
Something in here. Brain. Okay. Neurons. Neurons do what? Transmit what? Electric. No, now we're getting charged up, aren't we? What do you think memory is?
A bunch of
Stored charges.
charges.
Memory is stored charge. And you've done it deliberately. Placed the charge somewhere. And if you have a greater memory, you have a greater capacity to store and recall, right? Okay. I've stored a lot, but I can't recall a lot of it at this point, right? So, or it takes longer because of all the wires. There are too many wires up here. Okay, so the ability to store thoughts and actually doing so with electric charges. You're putting electric charges in some locations. You're altering things at a molecular atomic level. I'm not sure. I don't know what it is. So then you release them, go get them, bring them out of storage. The ability to store. And in electricity and magnetism, one of the things we're interested in is the ability to store charge. So your computer memories do it using magnetic memories or capacitive memories using electrical charge motion and not magnetic ways of storing the charges. Your brain does it. The ability to store charge. You can picture a physical analog, not exactly the same thing, but an analog if you want to think about the ability to store water. A reservoir. A reservoir supplies water for a city, for example. And you can take the reservoir and put it up on top of a hill or up on top of a tower. And the tower might need to be about how tall to be a good reservoir for a city? Well, how many stories are in a house? Depends on how many you're told, but usually it's 2 is a common one, or 1, right? Okay, so if you have 2 stories on a house, how high do the water pipes need to go? At 20 feet, right? 1 atmosphere's worth is 33 feet, so you need to go with your pipes, you need to be able to push water upstairs to take a shower if you have a 2-story. So a town needs to store its water in a tower that is at least as high as the rest of the buildings in town, and typically something like 60 to 80 feet, maybe 100 feet. Usually about 3 atmospheres is normal pressure in residential stuff. So around here we could store water up on tops of some of the hills, couldn't we? Are there any hills around here that have water storage places? Yes, right over here. The hills right behind campus have water reservoirs in them. And the water is also stored underneath us. We have one of the world's largest water reservoirs under Orange County. The entire county practically is on a giant basin that stores a huge amount of water, probably 5 to 10 years supply for the county. And then we pump it up. We pump it. We find a way to, using pressure and pumps, to put it through pipes. The ability to store charge, similar. We want to move charges from one place to another, and we will use the wires as our way of doing that. When we store the charges, then we can use them later because they can do work. If we put a bunch of charges, here's two charges represented by my fists, and they're the same sign of charge, we push them together. Do we have to do some work? We have to do some work to push them together. So they have the potential to do work, potential energy, if we release them. Now let's take billions and billions of these and put them together and push them, push them, push them. If we get them all stored in one place, we could then allow them to do work later. And speaking of billions and billions and billions, I turned to my wife last night and I said, "Guess what, dear?" And she said, "I'm certain I won't." And I said, "We have been together approximately 1 billion seconds."
Oh, that's gross.
And she said, "That sounds like a lot." And then what did she say? Remember about doing science? Trust no one, right? She said, "I'm not sure you got that right." And I said, "Well, it's 3.16 times 10 to the 7th seconds per year, and we're about 30 years. And she said, "Well, you sure you calculated that right?" Okay. All right, here we go. Let's store some charges. Oh, let's do that. Is there anybody I know you had the adrenaline rush from doing the quiz. Maybe somebody just wants to help in this moment. No, not yet? Okay, so then we're going to do this little, you've helped, you've helped, you've helped. You've helped. Have you, I see, you've said it with confidence like it's true.
It is true.
Have you helped, sir? Yeah. It's okay, you're safe, you're safe. Have you helped, sir? Oh, that was a quick dodge. Come on down. Let's go for it. It's your moment. It's coming out of your 14 minutes of fame right now. Have you helped? Have you helped? Okay, so not yet, okay? But be ready, okay? Live in fear. It'll happen. Okay, and you are?
Jasper.
Jasper? Hey. Cool. Okay. What we're going to do is try to develop some understanding of what it means to store charge, the ability to store charge. Come on over here, Jasper. Let's have you work here. Let's put you right up front, over here. Let's see if I can get this guy to here. Okay, so let's see. I'm going to put that like that. You're going to be over there. This is what you're going to work with, okay? And see this? It's got to stay attached there, okay? So, Jasper, I'm going to describe, because I've got the microphone, but you can then say yes, no, or add your own comments as well. What do we have here? We've got two square plates. Square plates, right? And what do you think they're made of? Good thinking. Metal. In fact, this is aluminum in American, right? Okay, so aluminum. And what's the dimensions of the plate? What are the dimensions?
20.
So about 20 centimeters by 20 centimeters. And about how thick is the plate? 2 millimeters on, is Jasper? Is that right? On Jasper's authority, 2 millimeters. Okay, so we've got a square plate, and is this one similar? That plate is similar that you can see here. So we've got two square 20 by 20 centimeter plates. Now, could we put charge on this? Sure, you could rub your feet along the carpet, come over and zap it, and here it is, and it'd have a little charge on it. Now what we're going to do is put it in here, and we're going to measure with this, and we're going to read on these dials. We're going to put this guy on, okay?
How far apart are the plates?
How far apart are the plates? We have a choice for that. There are several choices here. And right now I'd say it's about, what do you think, 3 millimeters?
Yeah.
About 3 millimeters apart. And also under Jasper's control is how much the plates overlap. That is, right now they're parallel and completely overlapping with the areas, and he can pull them out. So let's take a look at what happens here. Does this guy do anything when we did that already? So this guy's already on or not? Okay. So if we have the plates all the way in there, Jasper's going to do this thing now, and I read on this, what does that thing say up there? 200, providing, let's see what it's set to on, yes. Okay, so 200, and then you see the units listed underneath with a little p and a capital F. So that's 200 puffs is the way we say that, but it means 200 picofarads. So we're going to try to figure out what these units are as we develop a little physical understanding of the ability to store charge. So 200 picofarads, right? And we have two parallel plates separated by 3 millimeters that are 20 centimeters. You guys know Jasper? Okay, so you guys, do they take good notes?
Yeah.
Which guy takes better notes? Don't do that. Okay, you two guys take good notes. Let him look at both of your note sets to get his, okay? Because he's going to be up here a few minutes. Okay, so anyway, Jasper's up here and says 200. Oh, look at that. This guy over here says just a little over 200 also, doesn't it? So you can look at either one as you like. Almost changed my MGH. Okay, so now why don't you pull that guy out? Oh, push it back in. That means we better take some kind of measurement about the overlapping area and what it does. Right now we have 100% overlapping area. All right? So the area is 400 centimeters squared. And you got to convert that to meters squared. 0.04 meters squared. The ability to do it. It's not too hard, right? You can do it. Question?
I'm sorry, this is kind of a silly question. Can you repeat basically what's happening in terms of the wires from that going onto the plates? Like where exactly is it connected and what is it?
Okay, first off, the only silly questions in physics are the ones you don't ask. Okay, so if you ever ask a question in physics, it's not silly. And in this case, that's actually rather important, what you just asked. What you see up there is the wires go to the left. And maybe we have trained hamsters down below in the cabinet that take care of that. And your question is quite reasonable, right? It actually matters. The wires run. Jasper, give her a description since I just faked everybody out apparently. What do you see? Where do the wires run?
Well, the positive charge is going to the front plate, and then the negative charge is on the back plate.
So the red wire runs to the plate you can see with your eyes, and the black wire runs to the back plate, which is the one that Jasper can move. And then it runs over to the 1 meter that's on the overhead projector, and also separately to the meter that's down here with the giant needle, which doesn't show very well for your entertainment, right? It doesn't really, it's hard for you to read it, okay? Especially, can you read this one okay? All right, so what we have is the wires, and then there's some electrical thing in here, and little lights that go on and off, and an electrical switch. And what I'm asserting is that this is measuring the ability to store charge, and we're seeing that this one is 200 picofarads. Pico, what's a pico? Anybody know? 10 to the minus 12. It must be half a boo, right? Picoboo. Or that's a 10 to the minus 12 boo, right? That's a really small boo. Okay. I guess little kids do them, so that's okay. All right, so we have picofarad, 10 to the minus 12 farads. Farad, F-A-R-A-D, is named for somebody, and I don't know who, but that was their name. I never met them. Okay, now, let's make the area half as large by sliding that out, half. So it's only half overlapping. On Jasper's authority, is that half overlapping? Looks like it's a little bit, yeah, about half overlapping. What do we see the capacitance goes to? What's the measurement? What's the number up there? 120, isn't it? Okay. Can you go to a quarter overlapping? So only 25%. Yeah, okay. What do we see there? 75. Go to an eighth, 1/8. So we're doing factors of 2 here on everything, right? And oh, now it's down to about 50. 48, okay, cool. Now, pull it completely out. What's it go to?
0.
No, not quite, does it?
10.
About 10. So it didn't quite go to 0. So what we're observing here is that the capacitance decreases as the area of overlap between these two sheets decreases. Almost, let's see, go back to half was what? Half the area was 120 and full area was 200. So if we were thinking about what kind of simple model, we might say that this ability to store charge is proportional to the surface area that overlaps. And it's not quite right, is it? If it went from 200 and we went to half the area, it should have read 100, but it read 120. Then again, when we took it all the way to 0, there was still some needle reading, huh? So there's some uncertainty, go ahead, push her back in there. But it certainly seems reproducible. Okay, now let's try changing the separation, the distance of separation of the two. So we have right now about 3 millimeter separation, right, Jasper?
Yep.
What are you going to go to for your next one?
The furthest one?
No, we'll do them consecutively. Okay, and this one's kind of tricky because you got to do the bottom and the top at the same time, right? Okay, go ahead, push her in there. Let them get a number. What's the separation now?
4,
5, about 5 millimeters. It's a little hard to tell, but it's somewhere around there, right? 5 millimeters, and what do we get for the capacitance? 110. Okay, go for the next one, Jasper. And this one is about, you get them both, the top and bottom, yeah, okay. What do you think for that guy?
7.
Okay, let's go for 7 on Jasper's authority, and that's about 80, isn't it? Let's go for the next one. Now we've got, what do you think?
About 1 centimeter.
1 centimeter, right? And we have 62.37. You were reading it closer than I was, weren't you?
Oh,
Yeah. Okay, let's do another one. What do you got there, Jasper?
Probably like 1.2
1 point, you want to,
centimeters.
okay, 1.2 centimeters. What do we got up there? 51. You could make a graph of the capacitance versus separation of the plates, plate separation, or a graph of capacitance versus the area of overlap of the plates. And we've now just demonstrated some physical properties of the ability to store charge with Jasper's indomitable assistance. Thank you very much, sir. Oh. This must mean we need another volunteer. Madam, now is the time. And you are?
Caitlin?
Caitlin, come on down and help out. This one will be a thrill you'll never forget. Sorry about that. Okay. See, you were safe. You were safe, okay? So, Caitlin, let's see. Remember when we do the physics things, what's the kind of first thought that comes to most minds about doing physics, including physicists when they're doing it? I don't know. right? I don't know. And then as you're going along, what's the next thing you want to make sure you're doing? Trust no one. Notice those crossed arms. That's a good position for those arms, right? Because they're less likely to get blown off. Okay, come on over here. No, over here, over here. Okay, so are you comfortable and familiar with electrical devices? The answer is probably no. Do you use a hairdryer? Do you use a computer?
Yeah.
Do you use anything you plug in the wall? Do you stick your fingers into the wall socket?
No.
Have you ever stuck a toothbrush in the wall socket?
No.
Why not?
Because I don't want to play with electricity.
Oh, you guys. Remember, Darwinian selection does occur, so you need to do it within reasonable bounds. However, I'm not sure about the toothbrush at home, okay? So I don't think I would recommend that in general.
Okay.
I mean, using a toothbrush, yes, but not plugging it into the wall, because it might cause a little problem you're not expecting. Okay, so what do we see here?
It says caution, high voltage, danger when cover is removed.
Did you hear what she said? Okay, from here it says, it's upside down. That's what it says from here. If I go over here, it says, caution, high voltage, danger when cover is removed. High voltage, and it's written in large letters, isn't it? Kind of like it means it. All right, that's cool. I hope it's true. Okay, what we want to do, oh, let's look over here. Let's look at this guy. You ever seen one of these things before? Probably not. It's a meter. This one looks like it's about as old as I am. Okay? So the needle moves around. We're going to measure on this scale 1,000 or 5,000 volts V over here. Oh, he's put it on the 5,000 scale, hasn't he? Mm-hmm. That's neat. That's more voltage. Okay, we're going to charge this guy up, I imagine. Red light on the front. And we're going to let that guy charge. Let me see about this. Somebody did something. Oh, God. They had it down with like no volts. That's no fun. Okay, so now, is the needle moving?
Very slowly.
Very slowly. This needle is measuring the voltage on some capacitors here. This little bank of capacitors, and you should stand about there. This bank of capacitors is built to store charge. Now, the ability to store charge, everybody's got some. Your brain is using it, okay? Different kinds of capacitors can be made to store different amounts of charge. So we're storing some charge now. This is a power supply, this thing that I forgot. Caitlin says caution, high voltage. And what's it read over here? Go ahead and give them a reading.
About 10.5 kilovolts.
10. Let's see. I'm going to say
Or point.
1.05. Okay. So it's just a little over 1 kilovolt. Kilo means what? 1,000 volts, right? And what's the voltage you're used to in the wall from your house? Do you know? Say it again?
120.
Yes, correct, 120. And that's wiggling in time. So there's root mean square values or peak values. This one is a DC, direct current, steady in time, except that we're charging, so that steady in time thing is actually changing in time. Charging up to, what's it say now? About
the same.
And what does this guy over here say? So this guy has the wires connected up here, right? to these capacitors, and it's reading, oh, this is a little harder to read, isn't it? It's reading now about 850 volts. So the power supply is set to put out somewhere just a little over a kilovolt. The capacitors are charged up now to about 850. It's taking a while. Isn't that needle moving very slowly?
Yeah.
Oh, so the movement of the charge is taking, how long have I been jabbering down here now with Caitlin while we've been charging? How long? How long? We've got a couple minutes at this point, right? At least. What's it read now? Is it still getting a little more?
Yeah.
Okay. Yeah, okay. We're around 1,000 volts now, or is it 900? It's about 950 now. Okay. What we're going to do is I'm going to, for just hoots, we're going to turn some of the lights down now. Will there be other down? Okay. So let's put these things up. Get the screen control, lights. Turn that guy. Okay, so let's describe this. What is this that I'm holding here? And now, do you just keep your hands there?
Okay.
Okay?
It's like a long plexiglass
Long plexiglass rod with a
with a wire
with a wire coming
out
and
it's attached to the capacitor.
over at the capacitor. The wire's attached, right?
Yeah.
And there are on top of the capacitor sort of parallel sets of wires running along the top, right? Okay, you hold that. All right. When I say, there's only one thing you're going to do. Okay, when I say what you're going to do is touch this to there.
Okay.
That's it. Nothing else. Okay? Now, let's get the lights off so you can see a little more effectively what that does. I'm going to try that. Uh-oh. Uh-oh. Oh, my goodness. HAL 9000 is watching us. Okay. Go ahead, touch it. You just stay where you were. Just bring the right. Now, Caitlin, you seem to be a little more calm than normal.
Not on the inside.
Usually for this one, I get a short female because then I can estimate the frequency spectrum of the sonic exuberance. And then there's a scream, which has a lot of frequency components in the 1500 to 2500 hertz range. You're a very calm individual.
Sometimes.
I heard some short words from out there. A quick draw of the breath. Okay, now, here's what we do. You're going to touch it again now, but now what's the voltage?
Like half.
Half, maybe 500 volts, okay? Then when you touch it, I want you to show an element of surprise. So here's what you do. When you touch it and it goes flash, go Jeepers Creepers. You ready?
Okay.
Go ahead.
Jeepers Creepers.
That's the kind of thought that comes to mind, isn't it?
Yeah.
Okay. Touch it again. Not so much, huh? Touch it again. Only un poquito. All right? Go for it. Okay, now, do you want to let it charge back up a bit and have a little more thrill?
Yeah.
What would you like to say when it goes off?
I don't know.
How about yowzers?
Okay.
Is that a good one?
Sure.
Are you amped?
Yeah.
Does that galvanize your thoughts? Okay, what does it mean to be amped? To be, you guys heard that, right? Like when you were little, your parents used that kind of language, right? It means to be charged up, right? To be excited about something. It means you moved some electric charge. So this one you could really be amped, right? Okay, now what did we get to for voltage?
Like 400?
400? 500? Go ahead, hit it. Okay. Oh, Caitlin, that's the best response ever. Congratulations. Thank you very much. Oh, my goodness. Okay, now, when you have capacitors that have electric charge stored, they have the ability to do work. And we saw that some of that work was done. So you may notice also there's a pair of safety glasses here. So if you're going to be working near or not at a far enough distance where you might say, let's see, sparks may fly, right? Then you want to put safety glasses on because you got 2 eyeballs, most people, and you don't have a replacement set, right? So you want to be careful about things. Now, when that charge is stored there, it can reside in the capacitors for a sizable period of time. I've turned this sucker off, and it's still got a little charge in it. And even though I've discharged it now, it's still got a little charge left. And so what you do with things like this is you approach them, as I said, trust no one, right? Trust no one. And so when you come down here after the lecture, if you want to look at that thing, don't. Okay? And you notice I've unplugged it now, okay? Do you think there'll be some voltage here from the capacitors?
Possible.
Not enough. Okay, so now the trust no one, do you know how to test a radio battery to see if it's got good voltage, right? Is to put it on your tongue. The 9-volt battery works fine. Okay, now in my laboratory, people learn to make their own judgments for themselves. And we did a prank one time. We had a guy in the lab who was a little too trusting, so we gave him a 9-volt battery, had him test it on his tongue. A little bit later, we gave him a 45-volt battery. Yep, you could imagine. He did get a Ph.D., and he learned not to trust the other people in the lab after that. Caitlin, that was the best response I have ever seen for that one. That was just terrific. Okay, now let's see. We've got these guys stored charge. We got to get lights. Come on, all on. Let's get some more lights going here. Yeah. Okay, now we have motivated. We have seen that there is an ability to store charge. Turn it off. Close, mute. And HAL 9000 is not watching us now. Okay. The ability to store charge is done by placing 2, well, it doesn't have to be 2, it can be just 1 piece of metal and then moving some charge to it. Capacitance, capacity, right? Ability to store charge. The ability to store charge. How much work do we have to do to store some charge? The charge per amount of work done. Charge stored per amount of work done. So the capacitance can be described as this ratio of the stored charge divided by the voltage to which that system rose, or as we did things. So let's see. If we, example, Here's a sphere. We'll have a Canadian sphere. It has radius A. Okay, so this sphere, now let's bring a charge. We'll bring a charge in. Let's bring in a test charge. We'll bring in, say, a certain amount of charge. We decide how much. It's up to us. So we'll bring a test charge in from infinity. So this little charge goes in and is placed on that. The voltage on that sphere is this. That says then the capacitance of the sphere is the charge on the sphere divided by the voltage, Q test, over 4 pi epsilon naught, Q test, over A, 4 pi epsilon naught A. The ability to store charge is related to the radius of the sphere. And we've brought the charge in from infinity. So you can look at this and say, what's the capacitance of the Earth? It's a sphere. How big is the capacitance of the Earth? And then you can put charge on the Earth and store it up. And we do that. Sometimes the charge moves a little bit from, lightning moving stuff around. Sometimes it just moves around in the ground. Now let's take a look at what Jasper was showing us. And then we'll gradually build over to understanding what Caitlin was showing us. Let's take 2 plates. Two plates separated by some distance. And how do you do these things? Right? So on this guy, let's put plus sigma. On this guy, minus sigma. And that's coulombs per square meter on both of them. The ability to store charge, capacitance. The amount of charge stored divided by the potential between them. We can calculate each of those. The amount of charge stored, we can do pretty easily. That's sigma times the area. So we need to show in our drawing the area. Oh, but the voltage between them. Do we need to calculate that? Yeah, we don't know what the voltage is. See, the voltage is minus integral E dot dl. Oh, that's great. We don't know the electric field. Now we've got to find the electric field. So to find the electric field, integral E dot ds is the enclosed charge divided by epsilon naught. Then we can do our little plus sigma, our Gaussian surface here and here. Gets the electric flux there, E equals sigma over 2 epsilon naught from that guy plus the other one plus second plate. So E is sigma over epsilon naught between the plates, and it's 0 outside the plates, remember. Okay? So if we do that, we arrive, oh, what's that going to do for us? That says the capacitance for parallel plates because, let's see, we got Q over V, sigma A, over ED, sigma A, sigma over epsilon naught, times D. Now let's just take a quick little look here. Suppose A was 1 square meter and D was 1 meter. Can we imagine that? 1 square meter separated by 1 meter between the plates. Then C is 8.85 10 to the minus 12 farads. 10 to the minus 12 farads. 10 to the minus 12 for most things you're thinking of is a pretty small number, yeah? As in pico. 8.85 10 to the minus 12 picofarads. So this is only 10 picofarads, right? And I snuck in that the unit of capacitance in the MKS system is called the farad. You get your newtons and your meters and your seconds and your coulombs all worked out, and that's called farads in the MKS for capacitance. This says that you got to be clever to get the capacitance up to something bigger than this. And what we can do then, let's see, in general then, can we change epsilon naught? No, but we can change the properties of the material between the plates a bit. We'll work on this in a second using what Jasper did. We'll get a little bit further along on that. Can we make the area larger? And you might initially think no, because a meter is pretty good sized for working with things, right? But nobody said how that meter had to be laid out. So let's think a little more. Can we make the D, if we make D smaller, what happens to the capacitance? It goes up, doesn't it? And if we go from a meter down to a micron, that's a factor of 1,000,000. That would make that capacitance rise a factor of 1,000,000. And if we made the separation a micron, then we could take two sheets, lay them right on top of each other practically, right? And roll them up. And then they don't occupy a very big macroscopic space because we rolled them up. But then we get the area to be much larger if we want it to be. So if you get D as small as you can, then you can make A pretty big if you're efficient about rolling things up. Here is an example of such. This is shaped like a Tootsie Roll, isn't it? Okay, so it's a cylinder, and it's shaped this way because some person laid out a piece of aluminum foil, probably, then laid out a piece of insulation, and then laid out another piece of aluminum foil, and then very carefully rolled it up. Or a machine did it. And rolled it up into this shape. so that it's actually, if we unrolled it, it'd probably run to the back of the room. A very small separation between the plates, and then as much area of the plates as you can put in. And this is called a capacitor. Capacitor, the ability to store charge, is put into these devices called capacitors. So here's one kind of shape for that. Here's another one. They're often orange in color, but doesn't require that they be. And then they have, oh, this one's one of my favorites. This little capacitor in my hand, the one with the green plastic around the outside of it, says it has a capacitance of 1 farad. 10 to the 11th times that. Almost 10 to the 11th, right? 100 billion times. This thing has the capacitance of a farad, but it's close to useless. Well, actually not so much these days, but it used to be. Because if we make the distance smaller and smaller, what happened when Caitlin brought this stick down here? It discharged. It made an arc, didn't it? So at some point, as you bring two metals close to each other, at some point, there will be a breakdown, a spark, if you will. That spark happens. When that spark happens, now the charge that was on the two plates can mingle, gone away, no more capacitance. You did the work in the spark. So as you make that gap smaller and smaller, down towards 1 micron, you have to reduce the voltage to which you could charge it. We could do 1,000 volts here, but if we made the gap between the two sheets smaller, that voltage diminishes. This says 1 farad, and it only allows it to charge to 5 volts, which is useful these days. 5 volts. How far across is this? You could, in your mind, design this capacitor. You can see the size constraint that it's got to fit. What is it? 5 centimeter diameter, circle, 1 centimeter in total height. If it can charge to 5 volts without breaking down, can you tell me what the separation is and the number of layers in the sheets that are in here? Become a capacitor designer now, okay? They come in all kinds of different shapes, I guess. Here's a different shaped one. Okay, so we have the ability to store charge. This is a kind of general kind of way of looking at things. We got a very convenient D downstairs here. That came from finding the electric field using Gauss's law as having basically no distance dependence, gave us a 1 over D. What happens if we change our geometry to have a center wire and then a surrounding wire? So we could change the geometry on a capacitor . We could make a coaxial cable. If we make a coaxial cable and put some charge on it, this is a pipe carrying another pipe inside. A wire surrounded by an insulator. So this is wire out here, insulator, and inner conductor wire. So it's called, this outer one is called the outer conductor. This cable, the high voltage line right here that we use to charge that capacitor, is exactly that. It's got a center conductor down inside. Then, if you can see well enough, a little white, there's a plastic insulator, maybe Teflon or some kind of plastic. And then there's an outer conductor, which is often made of a braided wire. So that allows the electric field to build up in between, right? And we can calculate the voltage between the two. But now is the electric field constant as we move from one conductor to the other? No, it is not. The electric field is much stronger at the center, where the radial changes, right? If we look at it from the end, here's what we're looking at. You can see how the electric field lines get further apart. This is an end view. The electric field lines get further apart as you move radially outward. So the electric field is stronger on the inside than on the outside. The Gauss's law gives us then the dependence of the electric field versus position. We might get a logarithm for this one. Some geometries you might get a 1 over r for the potentials if it's spherical. But the key point here to worry about is the electric field at the inside is where it is strongest. So this kind of wiring is most likely to have the breakdown, the arc, happen at the center. You can't make this center wire be infinitesimally small because the electric field will get so large that it'll cause a breakdown there. So you have to design these wires with as big a center conductor as you can tolerate so that you can have the biggest voltages you want on these things. So this one will get, instead of just a 1 over d, maybe you get a logarithmic factor in there for some of these. So you should go through this process. Find the electric field as a function of position, then calculate the voltage induced across the gap. Then once you know the voltage, calculate the capacitance from the charge that you placed on it to make that electric field. Each of those steps reinforces what you already know about how to find electric fields, how to find potential energy, and then the ability to store charge. So break it down into those steps. Do it for this. This is done in your book in one of the examples. And this is a very common kind of wire. It's called coaxial cable. It's used all over the place. Your televisions use it from your, what do you call those, the dish antennas and things like that. I've got miles of that stuff in the lab. So you have to design with the capacity in mind. This little capacitor can only charge to 5 volts. Caitlin, how high did we charge this guy again? 900, around 1,000 volts, right? Quite a lot more. There are some things in my lab that you can charge to 1,000,000 volts or so. What's 1,000,000 volts amongst friends, right? It's a lot of fun, that's what it is, okay? Can you calculate what the charge was on the Van de Graaff generator and what voltage it got to? Yes, you can. And now what's the capacitance for that Van de Graaff generator? It was a sphere there, you know how to do that. Okay, let's see now. I think I need another volunteer. We need one more volunteer. Let's see, we've been working this side of the crowd. You've already helped, right? Yeah,
Yes.
I heard you. Have you helped, sir? Have you helped, sir? Would you care to join me at this point? Got to alternate them. Okay, and you are?
James.
James? Hi there. Hi there. Come on over here and give us a hand. Okay? All right, over here I think on that side would be good. Let's work back into this guy. How do we get this on? Try that. Try that. Maybe we need a screen. Okay, let's get you familiar with this. Once you pull that guy out and get it into see the slot, the closest one you can, and it has to be matched on the bottom. It's real easy to get them tilted a little. Excellent, okay. And then what do you see for capacitance?
200 picofarads.
200 picofarads, and that was what Jasper had, right? So we're on the same page with that. The only page we're lacking is figuring out how to get this thing to go. And I think the screen has to come on down. I do not have the capacitance to wait for things. There's another word for that. It's called English, and it's patience. I do not possess that. Oh, God. Oh, okay. Now, can we get the doc cam going? Yes. Do that. There we have light. Okay, James. We have the capacitor, again, that Jasper used, so 20 by 20 centimeters with what separation are we talking here? 3 millimeters?
Yeah.
Okay. Now, are you bored?
No.
This is cardboard. Are you bored?
Yes.
Okay. Now, take the cardboard and put it between the two sheets. And yeah, try different geometries. Just go slow. Just slow, 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 slow. Patience. There you go. Okay. Is it all the way in?
Yes.
Oh, what happened? It went off scale, didn't it? Let's try. That's not so satisfying. Okay. Let's see now. If we read, I changed the scale a factor of 10, so this is on a 3,000 puffs scale. What does that read right now?
So that's 300.
What do you guys read? Jasper, what do you read from back there? Get your eyes on the screen so that you have the same angle as everybody else. What do you get? It's a little over 300? So we've added a 0 on the numbers up there, right? So it's 300, 310, somewhere around there? Okay, now James, pull the cardboard out. And let's see, what's it read there? 200. It was just a little over 200 on the other scale. So we're okay then, right? Okay, and do you remember there was a movie called The Graduate?
I haven't seen that.
Yeah, your parents saw it, okay? And what was the key word in the movie? Plastics. What do you have there?
Plastic.
Okay. Put her in. Jeepers creepers. You know, it doesn't work for you either? Jumping Jehoshaphat. That one is about what? 410? Just a little under 500? 410, right? So the ability to store charge changed when James changed the material. If it was just air, 200. Put in the cardboard, what'd you get?
300.
300. And if you put in the plastic, what do you get? 400 here. So the material between the plates matters. Let's see if we can think that through just a little bit. If we put a material in here and we put an electric field on it, remember when you brought your arm near the Van de Graaff generator, the electric field pulled some hair towards it, didn't it? So evidently the electric field pushed some charge away and pulled some charge towards the source of the electric field. So the same thing goes on here when you put the plates between, when you put the cardboard between the two metal plates. It pulls a little charge one direction, pushes a little charge the other direction, and it gives you more ability to store charge by doing that. This is then something of the electric properties of the material, of the electric. That's said to be dielectric. Dielectric properties. And what you do on the capacitance, you'll have to memorize this because you weren't there to write it down, that epsilon naught in the equations for capacitance gets replaced with just epsilon. You erase the little zero subscript and you put epsilon of cardboard, epsilon of plastic. Now, let's see if we can do this in our head. The capacitance of the parallel plates, epsilon naught A over D. Did the separation of the plates change? When he put the plastic in, the plate separation for the conductors stayed the same. Yes, Emily? Got it? Right? Then he puts those guys in. The capacitance rose by 200 to 400. What is epsilon of the plastic compared to epsilon naught? Twice as much. The ratio of epsilon of the plastic to epsilon naught is 2. That ratio is called the dielectric constant. Kappa is commonly used. Kappa, dielectric constant kappa. So the dielectric constant of the plastic that he has put in here is approximately what? 2. Now do the cardboard. Dielectric constant of the cardboard is about 1.5 because the free space dielectric constant gave us 200 here. We are measuring the dielectric properties of materials. You never would have guessed that possibility existed within you today, and now you are empowered to measure the dielectric properties of materials. Extremely useful, okay? This will insulate you from all kinds of things in life. Gives you the ability, okay? And Caitlin in particular will understand the need to stay away from very high voltages that can cause large sparks, right? Okay. Any questions, James?
Nope.
That was with certainty. We must be done for today. Thank you very much, James. Appreciate it.